Okay, question 5. So we're looking for basically shear stress at point A and point B. So we're interested in shear flow. Start off there. Let's work out. So you're looking at using this equation. Here we've got the shear flow. We've got the shear force V. Q, we'll come to that later, but we're going to need the second moment of area for the section, so we don't know that. So let's start working out what that is. So second moment of area or a section, well, what we'd do is we'd double up and treat this as 2 squares. And that's, we need to apply the parallel axis theorem. So the distance from here to the center of one of these squares is going to be 100 millimeters. So we've got 2 of them. I'm going to do BD to the power 3 over 12 plus AH squared. And that's for my, I'll call this section 2, section 1. So that's for my section 2. And then I'm just going to have, because this is going to go through the neutral axis, BD to the power 3 over 12 for my section 1. So I want to put those numbers in. So you're going to have 2. You could do this in millimeters, to be sensible. 100 times by 100 to the power 3 over 12 plus area, which will be 100 squared, times by h squared, which will be another 100, so lots of hundreds squared. Okay, and then you'll want to do this now for the middle section. So its total width is going to be 300. The depth of it is 100, so you've got 100 to the power 3 divided by 12. Right, so put that in your calculator. It's going to be in millimeters. So I then convert the millimeters into meters, and I get 41.667 times 10 to the minus 6 meters to the power 4. So that's working out the I term. Now let's work out what the shear is for this point and then for this point. So here, this is when you're going to need to use your Q. So for the top one, what we can do is imagine that we've got just a block there, and we know its distance is 100 millimeters away. What I want to do is work out the Q for this block, because the B is sitting underneath here. So when you're looking for the shear flow, you need to cut it off at the position where you're looking for the shear flow, and then consider anything above it or below it. Easier to consider things above it. So Q is first moment of area. So it's the area of that block times by its centroid, which is the same as the H in this case. So we've got this distance from here to here. So Q will be, well, we could work in millimeters again, be careful, 100 squared times by 100. Then convert your answers into meters. Here you've got meters to the power 3, so for this case you would be dividing it by 10 times 10 to the power of 12, and here you're dividing by 10 to the power of 9. And you end up with 1 times 10 to the minus 3 meters to the power of 3. So that gives me my Q there. I'll kind of solve this problem in parallel. So that will be my Q for the point of interest at B. And now the Q for the point of interest at A. So this is going to be slightly more tricky. So here you could say that you could split this up as QA equals this lower section, Q lower, plus the upper section, QB, which we already worked out. So now we just need to work out what the Q lower bit is going to be. So the Q lower will have a width of 300. First, let's work out its area. It's 300 millimeters wide. And then it's got a height of 50 millimeters. And the centroid for this, well, if this is 50 millimeters depth, the centroid will be 25 millimeters. Okay, so remember we're going to divide that all by 1 times 10 to the 9. And then we'll add on our other area. So 1 times 10 to the minus 3 there. Sorry, second moment of area. First moment of area, sorry. And we end up with the answer 1.375 times 10 to the minus 3 meters to the power of 3. So I've got my two Q's. I can now plug my numbers into this equation, but this is the shear flow, and what we're interested in is finding the shear stress. Shear stress is given as the shear flow divided by the width of the section that you're trying to pull apart. So this is the width of this section, and this is the width of this section. So you've got Q divided by width, which is normally given T for thickness. So we are going to be plugging in V, Q, and its thickness in the horizontal section, IT. So plug your numbers in for the first one. So you've got 600 times 10 to the 3. So working out the shear at B, you've got a Q of 1 times 10 to the minus 3. You've got a width of 100. Well, actually, to put the I down. So the I is the same for both equations. So it's going to have 41.667 times 10 to the minus 6. And its width is just 100 millimeters. Okie dokie, so you then end up with something of the order 24.8 megapascals. Okay, so that's fine. And then for the other one, where your V doesn't change, so that's 600 still. Here, the section that's trying to be pulled apart is going all across this section here, so it's now wider. So that's going to be different. The I will be the same. And your Q will be different, so the Q will be that value there. And the width, so that's my T, will be 300 millimeters. And that works out to be 11.5 4 megapascals. So that matches up with this one here. So therefore I am reasonably comfortable that I've got the correct answer.